We are very happy to invite Professor Tristan Collins from University of Toronto to give us a talk on moment maps in mirror symmetry. Let's welcome.
Thank you. Well, thank you for the introduction. Obviously, it's an honor to be here. Very flattered to receive this FSA award. So, I'm going to talk about this stuff about partial differential equations that arise in mirror symmetry. So this talk is going to be, no real mathematics, just sort of discussion, pictures, some statements of theorems. I'm going to start with some motivation from mirror symmetry, and then I'm going to introduce the two PDEs that I'm interested in, namely special Lagrangian and deformed Hermitian-Yang-Mills equations. And then I'm going to focus mostly on this second one, this DHYM equation, and I want to discuss a variational approach to it. Actually, there's going to be very many similarities with some of the things that Boo discussed in the last talk before lunch. And then I'm going to discuss about how this variational approach can be connected with algebraic geometry, and in particular stability conditions in the sense of Bridgeland. And finally, maybe if there's time, which there almost certainly will not be, I'll end with some applications to symplectic geometry. Okay, so what is mirror symmetry? Well, mirror symmetry arose in the physics literature as some observation that one could construct two different types of string theory, type 2b string theory, on one Calabi-Yau and type 2a on another Calabi-Yau, and that these two theories were really the same in the sense that they were describing the same sort of physical universe. So each of these theories comes with a collection of things which they call d-branes, which as a mathematician you can sort of think of naively as some sort of particles that live in these physical theories. So in the type 2b string theory, these d-branes are associated with complex geometry, while in type 2a they're associated with symplectic geometry. So as a consequence, what you see is that because these two theories are supposed to describe the same sort of universe, they should have the same particles. So in particular, there should be some sort of correspondence between symplectic geometric objects in type 2a and complex geometric objects on some other Calabi-Yau in type 2b. So one way to think about this is in terms of, this is Koncevich's homological mirror symmetry proposal, is that one should think of this as an equivalence of derived categories. So namely, if you have two Calabi-Yau manifolds which are mirror, then the derived category of coherent sheaves on one should be equivalent to the Fukaya category on the other side. So this derived category of coherent sheaves you can think of as some set of things which are roughly vector bundles-ish. And the Fukaya category is something whose objects are roughly Lagrangians. So how to understand this correspondence was first, so there's a proposal by Strominger, Yau, and Zaslow for how to go from one Calabi-Yau to another in terms of, by understanding very fine properties of Calabi-Yau metrics. And you see that, okay, so I mentioned this fact that these two categories are describing all these possible particles, but there's sort of an overcount. So notice that, that of course the derived category of coherent sheaves doesn't depend on the symplectic data, and similarly the Fukaya category doesn't depend on the complex data. So not all of the particles in these two sets are really realistic. So there's going to be some sort of virtual particles where you've taken something, this is all a picture, right? This is not really rigorous, but you've taken sort of two electrons and just jammed them together into one particle. And of course, these things are repulsive. So this is not something you would ever see in your realistic theory of the universe, and this should sort of somehow decompose in these two constituent pieces. So the realistic particles are the ones which should sort of not decay. Okay, so that's some picture that you can have in your head, but how does one really describe this? So let me describe what these particles are supposed to be on the symplectic side, first of all. So here we have this Calabi-Yau manifold. So these are the structures. So capital omega is the holomorphic volume form. Small omega is the Kähler form. You have the complex structure. So we say that a half-dimensional manifold, so this is, this Calabi-Yau has real dimension 2n. So we're looking at real manifolds of dimension n inside of X, which annihilate the symplectic form. Those are called Lagrangian, and they're special Lagrangian if they also satisfy this, this condition with respect to the holomorphic volume form. So this is a special type of the theory of calibrated submanifolds due to Harvey and Lawson. And such things are automatically volume minimizing. So that was one of the sort of interests of in these objects in the original literature, was that this was a way of producing objects which were volume minimizing in their homology class. So these, it turns out, these objects, so these Lagrangians, are supposed to be the sort of stable, the things which describe stable particles. So these are the D-branes, which are somehow supposed to source, you can think of as particles which don't decay. So, so very roughly, right, these, this Fukaya category parameterizes all these Hamiltonian deformation classes of Lagrangian submanifolds. And we say that a class in this, or an object in this category is stable if it can be deformed by Hamiltonian isotopy to a special Lagrangian representative. So these are somehow the things which are sourcing all this stuff that we see in our physical theory. Right, so I said this thing about volume minimizing. Right, so let's study this, this special Lagrangian equation. So this is a PDE for an embedding, right? So let's study it in the simplest possible example, namely in R2n. So, which we think of as Cn with its standard Calabi-Yau structure. So we're going to consider a graph. So we're looking at a map from Rn into R2n, which is just some graphical thing. So this graph turns out to be Lagrangian if and only if it's given by the gradient of some function, some real valued function. So you see, this is one of the advantages of working with special Lagrangians. Ordinarily, minimal surfaces would be described by n functions, even for graphs. And here you see that they're described by one parameter, namely a single real valued function. But the equation becomes sort of a somewhat higher order. So this special Lagrangian equation becomes sort of quite nonlinear. You take f, you look at its Hessian, it's got some eigenvalues, and you sum the arctans of the eigenvalues of the Hessian. And the special Lagrangian equation is saying exactly that sum is constant. So this is a fully nonlinear PDE now. Okay, so that's the special Lagrangian equation. So this is the simplest model of a PDE, which is describing some sort of canonical geometric object which arises in this physical theory. Again, you can imagine that this is in some sense the local model for special Lagrangians always, although that's not quite true, but let's just imagine. Okay, so what about on the complex side? On the complex side, these D-branes are parameterized by coherent sheaves, or the things in the bounded derived category of coherent sheaves. So which you can think of as morally as vector bundles or possibly complexes of vector bundles. So I want to consider just a simple object, which is a line bundle supported on a complex subvariety. So this subvariety could be X. I'm not requiring that it's a proper subvariety, but so this is a thing that lives in this derived category. So the equations of motion for these objects were derived independently by Marino, Menasian, Moore, and Strominger, and Lung, Yau, and Zaslow. So Marino, Menasian, Moore, and Strominger from the physics point of view, and Lung, Yau, and Zaslow using the SYZ technique. And the equations are this, are what are called the deformed Hermitian-Yang-Mills equation. So, so the deformed Hermitian-Yang-Mills equation is an equation which seeks a metric, a Hermitian metric on this complex line bundle, such that when I take the curvature of this metric, so this is an imaginary 1-1 form. So then I look at omega minus f, so that's now an imaginary 1-1 form, and I take its top wedge power, and I require that the imaginary part of that up to this e to the minus I theta hat is 0. Okay. Sorry? I want to just study smooth. In fact, I'm going to focus mostly when d is x. But yeah, in theory, it could be singular. Yes. Yeah. But then the PDE doesn't really make sense. Yeah. Okay, so this is the equation, and you see, we'll see that this is very similar to the special Lagrangian equation. So this is really a complex analog of the special Lagrangian equation. Okay, so these are the PDEs that describe these objects. There's also an algebraic approach to try to describe these objects, which goes back to work of Douglas and Thomas Yau, and then subsequently Bridgeland, which is that the existence of these objects, so special Lagrangians or solutions of the deformed Hermitian-Yang-Mills equation, is supposed to be equivalent to some purely algebro-geometric notion of stability. So one can think of the Donaldson-Uhlenbeck-Yau theorem as some sort of guiding principle. So the present version of this folklore conjecture is the following, which is saying that solutions of these PDEs exist if and only if the corresponding class in the appropriate derived category is stable in the sense of Bridgeland. So I'll probably come back to what this means later, but this is some sort of notion of stability. But it's sort of maybe important to point out. So on the symplectic side, there are very detailed conjectures made by Joyce telling you exactly how this Bridgeland stability condition should somehow emerge from singularities of the Lagrangian mean curvature flow. But maybe it's important to point out that these Bridgeland stability conditions are not really known to exist in general. So the existence of Bridgeland stability conditions is a very hard problem to solve. So really one should view this as sort of a nested sequence of conjectures. First, that these stability conditions exist, and secondly, that they say something about existence of solutions to PDEs. Okay, so so I want to focus more on this deformed Hermitian-Yang-Mills equation. So I'm going to look on the complex side. So let me say what this equation is. So we have our Kähler manifold. I take some real 1-1 class, which you can think of as the first term class of a line bundle, if you like. So then the question that we want to solve is, can we find a representative of this 1-1 class such that this equation holds, where this zeta is e to the I zeta is some fixed constant in S1. Okay, and this constant is determined, okay, if this holds, then you just integrate this equation over the manifold and you get some number that depends only on the classes. Right, and so this number is determined by this cohomological condition. So you integrate this complex 1-1 form, it gives you a complex number, and you take the phase of that complex number. Assuming it exists, this integral could be 0. Okay, and this is equivalent to the equation that I wrote before, just by taking A to be minus the first term class of L. Okay, so what is this equation? Well, we can rewrite it in terms of local coordinates. So we take alpha, this 1-1 form, we raise an index using the metric that gives us a Hermitian endomorphism. In particular, it has eigenvalues. Okay, and then this deformed Hermitian-Yang-Mills equation is that the sum of the arctans of the eigenvalues is equal to a constant. And this constant is necessarily determined by this topological information zeta up to multiples of 2 pi. Okay, so you see that this deformed Hermitian-Yang-Mills equation is some sort of global complex geometric analog of the special Lagrangian graph equation. Okay, so there's an important thing to note, which will come up later, which is that if I can solve this equation, you see I am summing arctans of eigenvalues. That's a sum of some numbers. That's a number which is between minus n pi over 2 and n pi over 2. Since there are n eigenvalues, arctan is between minus pi over 2 and pi over 2. I get something which is between minus n pi over 2 and n pi over 2. On the other hand, this topological information, this e to the minus I zeta, is really only determined as a point in S1. Right, so somehow when I compute this integral, I just get the information of e to the I zeta, whereas if I solve the equation, I get the information of zeta. So that's some non-trivial information there, which will come up again later. Seems like a minor thing, but actually turns out to be quite an interesting feature of this equation. Okay, so here's this special Lagrangian graph equation again. Right, so I mentioned this before. Okay, So what do we know about the solvability of this equation? Well, it turns out that this equation, the analytic properties of this nonlinear PDE are very different depending on what area, sort of what the phase, the right-hand side is supposed to be. So when the angle is very large, namely bigger than n minus 2 pi over 2, so that's in the top branch of, so, you know, that differs from, the maximum it can be is n pi over 2. So this is somehow in the top interval of length pi. So then we proved, so in this case, the PDE is pretty well behaved. It's a concave elliptic operator. And so we can prove existence of solutions assuming a sort of subsolution condition. So namely, that you have this condition. So I have some other representative of the class where every time I remove one eigenvalue and sum the remaining eigenvalues, I get something which is bigger than this target angle minus pi over 2. And then there's this technical condition that the sort of phase of this thing, which you can think of as some sort of subsolution, is supposed to be bigger than n minus 2 pi over 2. Okay, so that was what we proved. So I should say that by a lot of hard work, Chaoming Lin has shown that this second condition can be dropped, which we conjectured, at least in maybe only in low dimensions, but anyways, it doesn't matter. So this condition B can probably be dropped in general. I think Lin has proved it maybe up to dimension 5 or something like this. Okay, but this is, I mean, some sense, like, satisfying analytic statement. These conditions are necessary and sufficient, but they're not algebraic. So if we want to obtain algebraic conditions, we need to do some more work. Okay, so how do you do this? Well, it turns out that there's a variational approach. So now it's gonna look very similar to Boo's theorem, but the formulas are gonna have more real and imaginary parts. So let's fix some representative of this class A. Then any other representative in this class can be written as alpha naught plus IDD bar phi for some function phi. So now we're going to study this set h theta hat, which is all the functions, all the smooth functions, such that the angle of this representative alpha phi differs from some target by minus pi over 2. Okay, so this is like this, in some sense, the analog of the space of Kähler metrics in this setting. And theta hat is just some possible lift of zeta. So this equation, this set a priori has sort of many disjoint sheets. Okay, so in theory it could look like this. You sort of have h theta minus 2 pi, etc. Okay. It turns out that there is at most one of these which is non-empty. So in fact, this picture doesn't happen. So there's at most one which is non-empty. It could be, in fact, that this set is just empty. So we don't know that it's not. This is sort of like the analog of this equation for this problem of a class admitting a Kähler representative. Okay, so if it's empty, then of course no solution of DHYM exists. And it turns out that you can turn this space H into an infinite dimensional Riemannian manifold. So this is going to look pretty similar to what was in Boo's talk. So I just take the, so the tangent space, this set is an open subset of the space of smooth functions. So its tangent space is just smooth functions. And I can define an inner product by integrating I take basically the L2 inner product, but with respect to this nonlinear volume form, which is the real part of this thing. Okay, and this condition on h theta hat is exactly the condition which makes this expression a volume form. Okay, so on the symplectic side, the analog of this would be the fact that the tangent space to Hamiltonian deformations are real functions on the Lagrangian, and I would be integrating the inner product of two Hamiltonian two objects in the tangent space to Hamiltonian deformations against the real part of e to the minus I theta hat times omega, where omega is the restriction of the holomorphic volume form. And this condition on the space H is exactly saying that L is what's called almost calibrated, which means that this real part restricts to a volume form. Okay, so this is this space. So it turns out that this makes the space into a sort of infinite dimensional Riemannian manifold. It's negatively curved, so very similar to the case of Kähler metrics. So from now on, I'm going to assume that this target angle that we're working on is actually in the largest branch. So it's between n minus 1 pi over 2 and n pi over 2. And this will come up later for PDE reasons. Okay, so associated to this Riemannian structure, there is a notion of geodesics, right? Which we'll spend some time discussing. But let me first explain why this notion of geodesics is important. So it turns out that there's a one form on this space, H, which you get by just taking a tangent vector and integrating it against the thing whose vanishing would be the deformed Hermitian-Yang-Mills equation, right? So if this thing is 0, then we've solved, if this thing is 0, then we've solved the deformed Hermitian-Yang-Mills equation. So definitely this is a one form whose vanishing is equivalent. So if this one form is 0 at a point, then we've solved the deformed Hermitian-Yang-Mills equation. So it turns out that this integrates to a well-defined function. So then trivially, critical points of this function J are solutions of this DHYM equation. And perhaps more surprisingly is that this function J is convex along smooth geodesics in the space H. So what's going on here is that this is like the Kempf-Ness functional for some infinite dimensional GIT problem, which I won't mention. Okay, but now we're in this sort of exactly the same picture that Boo mentioned in his talk. If we want to solve this, DHYM equation, we're looking now for critical points of convex functions on some infinite dimensional space. Okay, but there is one issue here is that when you do this calculation for the convexity, of course, you have to assume that everything's differentiable enough times that the calculation makes sense. So you need at least, well, better than C2 regularity for this calculation to really be rigorous. So the point is that at least formally, right, we can now try to approach the existence of solutions to DHYM as the problem of finding critical points of this convex function, which now becomes you can make the following picture. So here is a good picture, right? This is the space H. We have this convex function. We have this nice solution of the DHYM equation. But of course, your convex function could also look like this, in which case there's no solution of the DHYM equation. And then there's a sort of borderline case where it's flat, right? Has some flat direction. Okay, so what distinguishes these two pictures is the slope of this function near the boundary of H. So you can imagine I take my function, I look at its slope as I go off towards the boundary of H. You can imagine that maybe if you could prove that that was positive in all possible directions, you would conclude that this convex function was proper and hence had a critical point. So you cannot quite, anyways, yeah. So this is the sort of strategy, right, that we're going to try to execute. So you have to do the following three things. So the first is to prove existence of geodesics. And these geodesics need to have enough regularity that you can make sense of the convexity of this functional J. The second thing you need to do is you need to make sense of what it means to go to the boundary of H. So that's not a priori obvious. And then you need to understand what they're how to connect what it means to be on the boundary of H with algebraic geometry. Because after all, we're trying to extract algebrogeometric invariance. And then we need to actually produce geodesics going to the boundary of H and evaluate this limit slope in terms of some algebrogeometric invariance. So these are the three things we're going to do. And then maybe the fourth step is to try to understand how these invariants, whatever you get out of this calculation, how are these connected to this Bridgeland stability picture? Okay, so the geodesic equation, right? So as in Boo's talk, you compute this geodesic equation. You can rewrite it in terms of an equation on a complex manifold of dimension 1 higher. So you take x cross an annulus. And then you basically want to solve, okay, so this looks very much like the deformed Hermitian-Yang-Mills equation. You see, it's just the same expression, except now I have this n+1 because I'm on an n+1 dimensional manifold. And I just want an S1 invariant solution of this boundary value problem. So I have a manifold that looks like x cross an annulus. I'll copy Boo's picture of x cross an annulus. And I just want to solve, I have a boundary value problem, so phi0 and phi1, and I want to solve the deformed Hermitian-Yang-Mills equation on this manifold with boundary with this, given boundary data. But there's a wrinkle, which is that you see this pi star omega is only positive along the fibers, only positive in the x directions. It's 0 in the t directions, or in the base directions. So this is actually a degenerate fully nonlinear elliptic equation. So that's analytically difficult. Okay, so so the thing to do if you want to try to understand geodesics is to try to approximate it by some problem which is not as difficult, which is this regularized version of the problem. So I take my degenerate Kähler form, I add something, a small multiple of the Kähler form from the base directions, and I call this an epsilon geodesic. Yeah, right. Yeah, so this is an epsilon geodesic. And this is now it's elliptic, it's fully nonlinear, but it's elliptic and it has it's a boundary value problem. So then the idea is to try to solve this equation and produce estimates which are good enough in epsilon that you can take a limit as epsilon goes to 0. So this equation on the real side, so for Lagrangian graphs in a domain, so this is studied by Rubinstein, Solomon, Tamash, Harvey Lawson, and many others. And so this is motivated by earlier work of Solomon in the setting of symplectic geometry. And this sort of result of these works is that in the domain case, you can prove existence of continuous geodesics. So you can find a function phi which solves the real analog of this equation, which is continuous. So it solves the equation in the sense of, well, in many senses, a sort of viscosity theory. So you have a little bit better regularity than this, but essentially this is the main result. So for our application, this functional J depends on two derivatives. So it seems like having continuous geodesics is not enough to prove that this functional J is convex. It's not obviously. Okay, so so we need to do something more. So what we do is study this epsilon geodesic equation, and what we prove is that in fact you can find C1 alpha geodesics. So between any two functions in this space H, you can find a C1 alpha. In fact, it's even C1 more or less C11. So DD bar is bounded in L infinity, and this is enough regularity to prove that this functional J is convex. So how do you do this? Well, I'm just going to say a couple of words about this because I think as a PDE problem it's quite interesting. So the idea is that, well, instead of working with this degenerate metric, you just rescale the whole picture, so you're working on with the usual metric, the standard metric, but on a very thin annulus. So now I'm working on a manifold that looks like this. So I have x in this direction, but this distance is sort of epsilon. And then I try to solve this boundary value problem. So this is now the standard deformed Hermitian-Yang-Mills equation, boundary value problem. but on this very thin manifold. Okay, so, and then what you need to do is show that, that you can produce estimates which are sort of have the right scaling with respect to epsilon. And so, right, so this, okay, so if you think about it, you have phi 0 and phi 1 here, right? You have a function, you can imagine you have a function which is going from 0 to 1 in distance epsilon. Its derivative should be roughly of size 1 over epsilon, right? So here's this estimate, right? Its second derivatives should be of size 1 over epsilon squared, okay, since you're going from some distance, epsilon. But so now you are quite worried. So these are things which have to be true. But now it seems quite bad because you have a solution of a nonlinear PDE, and at least one of the eigenvalues of this solution, of the Hessian of the solution is gigantic. It's of size 1 over epsilon squared. That seems very bad because you would expect that if you have a solution of a nonlinear PDE, somehow the eigenvalues should all be coupled to one another. But this turns out to not be the case. That actually, if you look just at the spatial direction, in fact, all the derivatives are uniformly bounded. So this is quite surprising to me. Yeah. So and this is exactly what you need to pass to a limit after rescaling. Yeah. So once you have these estimates, then you can just take a limit as you rescale, take a limit as epsilon goes to 0, and you get this C1 alpha and dd bar in L infinity. Okay. So this is where a lot of the hard work goes in, is to proving the existence of these geodesics. Right. So much better than you would expect because of this behavior of the derivatives in basically all directions except the spatial direction is essentially sharp. And so one would expect that this maybe propagates, but in fact it doesn't. Okay, so back to the variational point of view. So remember I had this functional j, well, which was the imaginary part of something, but actually it turns out that you can just consider this complex valued function. So now this looks like the complex version of the energy that appeared in Boo's talk, right? Some sort of complexified version of the Monge-Ampere energy. So this functional turns out to have, you can sort of take real and imaginary parts of various multiples of this, and they will have nice convexity and concavity properties. So this is the one that's related to whose critical points are solutions of the DHYM. So that one's convex. But you can also take the real part. So that's affines. This is analogous to a result that was originally observed in the symplectic, originally doing the symplectic literature to Solomon. But then there's this other weird version, which is that you just multiply by the largest thing you can, and that functional turns out to have concave real and imaginary parts. You have in fact, four functions which have nice properties along these geodesics. We're going to use all of these functions to deduce necessary properties for existence of solutions. Okay, so now we have geodesics, and the next step is to construct these curves going to the boundary of H. So to do this, you take a nested family of coherent ideal sheaves on X, and now I'm just going to write something down. I take the generators of these coherent ideal sheaves, and I write down this function. Okay, if this is the kind of thing where if you know where it comes from, this will be clear why I wrote this down. And if you don't know, I'm not going to try to explain it. But this is for people who work in the field, this is sort of not surprising. It's some sort of Bergman kernel kind of thing. Okay, so I write down this model function. This gives me a curve, which is going as t goes to 0, right? You see as t goes to 0, this function is becoming singular and it'll have singularities exactly along the sort of support of these ideal sheaves. Okay, so this gives me a curve in the space H, if I take a sufficiently small multiple. And as t goes to 0, it becomes singular. So in particular, this is in any reasonable sense a curve which is going in some sense to the boundary of h as t goes to 0. But it's not a geodesic, it's some sort of model curve. So maybe draw it looking like this. Okay, so now the idea is that you use the existence of geodesics, you start shooting geodesics at this curve. And then the idea is that this, I mean, okay, so we only produce these geodesic segments. What I really want is a geodesic ray, but it turns out that you sort of don't need it as long as you can produce segments. So you produce these geodesic segments, and then you can, this behaves as, in every reasonable way, like a geodesic ray. So in particular, I can evaluate the slope of the J functional along this sort of sequence of geodesics. So I have these 4 functionals, J, C, Z, and I can compute their limit slopes by hand using resolution of singularities. So now let me assume that this 1-1 class is coming from the first Chern class of the line bundle, just to make the formulas look a little bit nicer. Okay, so what do we get? Okay, so now the picture is the following. So I have this, so let's assume that I have a solution, right? So here's my solution of the dHym equation. I have this model curve that's going off to the boundary, and I'm looking at J. So if I have the solution, then the slope of J along this curve necessarily has to be positive. Okay, so what I'm going to deduce then is obstructions to existence of solutions. Namely, if I have one of these curves where the slope is negative, then I know there's going to be no solution. So what we conclude is the following thing. So you take a log resolution of singularities, you compute these 2 numbers. Okay, so this is the integral over the exceptional divisor of this resolution of singularities. I take the class L and I perturb by a small multiple of the exceptional divisor, and I compute this integral. And then I compute the same integral just over x. So this is something which is given. So then we can make the following conclusions. So if there is a solution of dHym, then the imaginary part of the ratio of these 2 numbers has to be non-negative. And in fact, it can only be 0 if the geodesic was somehow just trivial. Okay, and then you also conclude that if this space H is non-empty, then the imaginary part of both of these numbers needs to be strictly positive. Okay. So let me draw the picture. So in this, the simplest case of this is when you just take an ideal, which is the ideal sheaf for some reduced irreducible subvariety, and you extract the dominant term as delta goes to 0, right? There's this parameter delta in this formula. So I'm just going to take a limit, extract the dominant term as delta goes to 0. And what you get is these 2 formulas. So you can compute these by some version of growth and decay Riemann rock or something like that. So this is just the integral, right? Here you're just taking this quantity e to the minus I omega ch of L, and you're integrating either over v or over x. And then the condition is that the imaginary part of this zv has to be non-negative, and the imaginary part of the ratio has to be non-negative. So this is easiest to see in terms of a picture. So I'll just draw this zx of L in the upper, so it has to lie in the upper half plane. This is zx of L. So stability, existence of solution means that for any subvariety ZV has to be in this gray region. If it's on the right-hand side, then there's no solution of the dHym equation. And if it lies in the lower half plane, then in fact there's not even one of these almost calibrated representatives. Right, so this gives necessary conditions. And then there's some Chern number inequalities, which I will not go into. But so we sort of conjectured that maybe optimistically that that this would be enough, just checking these special invariants for very simple degenerations. And it turned out, so in dimension 2, this was true. And this is just a consequence of Yau's theorem and like the Demailly-Pound characterization of the Kähler cone. There are also these Chern number inequalities which play a role, which I will not discuss. But then it turns out that the conjecture is true, at least in the dimensions where all the necessary pieces have been evaluated or been constructed. So the major progress in this direction was made by Gao Chen, who also spoke about his FSA winning work on this problem earlier in the week. And then there was a bunch of contributions by many other people to sort of remove various assumptions in Gao Chen's work. Namely, Chen proves really a sort of so assuming a uniform version of the stability, he proves existence and some sort of interpolation property. And then the uniformity was removed, and this interpolation property was reduced to the Chern number inequalities in dimension 3. So we know this conjecture, in fact, in dimension 3, which is quite interesting. So let me now discuss the relation to bridge instability. So remember, what we wanted to understand was this folklore conjecture. So what we did was we started with the PDE. We asked the PDE what had to be true if we could solve it. We derived these algebraic inequalities, these algebraic obstructions, and now we want to ask how these algebraic obstructions are related to the notion of bridge instability, which is supposed to appear in the folklore conjecture. So what is a bridge instability? Well, a bridge instability condition, first you need it's called a central charge. So this is the sort of one which is originally proposed in the physics literature, which should look pretty familiar. So you take an object in the derived category, and you just evaluate the integral of e to the minus I omega times the Chern character of e. This gives you a complex number, maybe 0. So very roughly, a bridge instability condition is a lift of the phase of this. So if this complex number is not 0, it has a phase, right? It has an angle. And a bridge instability condition is very roughly a lift of this angle from S1 to R for enough objects, satisfying some additional very complicated conditions. So in particular, it's an assignment to a sort of subset of objects in the derived category of a phase, which is determined by this central charge. And this phase has to satisfy some conditions. But the main thing for us is that that being stable is equivalent to inequalities for this phase. So an object in this derived category is with phase in 0 pi is bridge unstable if for any other object with phase in 0 pi and any surjection, the phase increases. So that's this picture, right, which should again look pretty familiar. So equivalently, if you want to, right, so this would be an unstable object, so that it has some quotient object with smaller phase. Okay, so this looks very, very promising because we have these similar kind of obstructions arising, which you should think of. I mean, the natural thing to do is assume that these obstructions are arising from some surjection of L onto L tensor, a skyscraper sheaf supported on V. But this central charge, this Douglas-Bridgeland central charge, is not equal to this invariant V that we computed from the DHYM equation. So you might think, well, maybe they're not that different, and the stability conditions you get from these two invariants are really the same. Maybe they're you know, the numbers aren't the same, but the stability conditions are the same. That turns out not to be the case. So with Yun Shi and then with Jason Low, who I missed the letter, but with Low, Shi, and Yao, we've been trying to understand whether these notions of stability that we get on the one hand from this infinite dimensional GIT construction, on the other hand from Bridgeland stability, whether these are really equivalent. So the easiest place to do this is in dimension 2, because in dimension 2, Bridgeland stability conditions are quite well understood. We have a plethora of examples of them. There's general theorems proving existence in general. So the first interesting case is the simplest possible manifold you can think of, which has more than one line bundle. So that's the blowup of P2 and a point. So in this case, Arcar and Miles studied Bridgeland stability conditions. And with Yun Shi, we showed that in this example, if you admit a solution of the DHYM equation, then you're Bergson stable. So you can think of this as being some sort of numerical condition for Bergson stability. But we also showed that there are examples of Bergson stable line bundles which do not admit solutions of the DHYM equation. So in this case, existence of solutions seems to be a stronger condition than Bergson stability, at least for line bundles. Okay, but then you might complain this is too simple. Maybe this is something to do with the fact that you're on a Fano manifold and these conjectures are all really about Calabi-Yaos. And that's a fair complaint. That's certainly a concern that I had. So then we studied more complicated examples, namely looked at some K3 surfaces. So for K3 surfaces, we again found examples. So you consider a particular, so Weierstrass elliptic K3, and you look at line bundles which are in the span of a section in the fiber class. And it turns out that, okay, if the fiber degree is always 1, then those are always Bergson stable. There's just no condition, right? These are just always Bergson stable. On the other hand, there are tons of these which are not GIT stable, and they don't admit solutions of the DHYM equation. So that is basically where that stands. So we're not sure. I mean, in these two very special examples we've studied, it seems like Bergson stability is a weaker condition than existence of solutions to the DHYM equation, but we really, I mean, there's no evidence that that should be true in general, but maybe it's like some sort of guiding principle for now. Okay, so what about symplectic geometry? Well, you can take this whole construction, and at least in cases where SYZ works, you can just turn it into theorems about symplectic geometry. So the cases where SYZ works on the nose are basically for toric Kähler manifolds. And then the mirror of a toric Fano manifold is then is what's called a Landau-Ginzburg model. You can think of Y as basically the moment polytope, and W is some sort of holomorphic function on the moment polytope. So yeah, Y is a torus vibration over the moment polytope. Okay, so then you can study special Lagrangians in this setting, and you can just do everything literally by hand. You can do calculations, and what you see is that if you take one of these geodesics that we wrote down before, and turn it from a degeneration in the space of metrics into a degeneration in the space of Lagrangians, you get these kind of interesting pictures. So here's a specific example on P1. So you get a family of Lagrangians, which are the graph of this interesting looking functional. And they do the following thing. So you have a sequence of Lagrangians which look like, so L0 is the initial Lagrangian. I start deforming this factor. I get a Lagrangian which sort of becomes very steep, and then very steep at the end. And then in the limit, this part that's getting really steep sort of disappears. It just bubbles and becomes this dark blue line. So this gives a family, this gives what you might think of as a sort of, in some sense, as a test configuration in the space of Lagrangians or something. And then the associated slope is an abstraction to L0 being deformable to the appropriate notion of a special Lagrangian in this setting. So one should try to interpret the resulting stability condition in terms of the Fukaya category, which in this setting is constructed, but that turns out to be kind of complicated for various reasons. But I should say that that actually recently, very recently, in the last 3 or 4 months, there was a nice paper of Stoppa where he sort of pursued this idea, and I mean, building on what we've done, but not really using it directly, and proved some very nice results about existence of special Lagrangians in this setting. Okay, I'll stop there. Thanks.
Okay, any question?
Thank you. Tristan, you mentioned that in this construction where you get the stability condition, you're able to bypass construction of this ray in this one. Have there been any updates on that regarding the construction of this ray, which I suspect...
Of actual rays? Yeah, no.
Nonsense.
Yeah, I think it's an interesting problem, but yeah, as far as I know, no.
Yeah. All right. Thanks.
Yeah.
Any further question?
So what kind of transverse inequality is coming to the play?
Aha, yes, excellent. Okay, so it's very interesting. I'm glad you asked. So the way that Chern number inequalities come up is the following thing. So the thing you should object to with what I said is that there's this phase that plays a role, this theta hat. And I never addressed, so if you want an existence theorem which is really purely algebraic, I have to tell you how to compute that angle, that lift from S1 to R. I have to tell you how to compute that number without assuming existence of a solution to a PDE or something. And so the way that you do that is you interpolate with something that you understand. So you consider a curve. You integrate over x of minus e to the minus square root of minus 1. And now I put a t omega ch of L. So this gives me, so I'm going to imagine t running from, t is going to go from plus infinity, which you can think of as some sort of large radius limit, to 1. So this gives me a curve, which is in C. Okay, so if I want to, so what we propose is that this lifted angle should be computed by computing the winding number of this curve. So I just follow this curve and I look at how many times it goes around the origin. In order for that to make sense, I need this curve to never go through the origin. And so the Chern number inequalities come from requiring that this curve never goes through the origin. So for example, in dimension 3, it looks something like, so C3, oh, maybe I write, so it's a line bundle, so it's hard to, but something looks like CH3 less than or equal to CH2 dot omega CH1 dot omega. I think this has an omega cubed. Something like this. So in fact, these are exactly the Chern number inequalities which appear in the work of Bayer-McCree-Toda on existence of Bergelind stability conditions on threefolds. Yeah. And what we prove in a paper with Shi and Yao, we prove that if you admit a solution of the DHYM equation, then this inequality holds. So this is a necessary condition for existence of solutions. And then in higher dimensions, it becomes much more complicated. So in dimension 4, Han and Jin proved that this gives an algorithm for what these things should be, these inequalities should be. In dimension 4, they were proved by Han and Jin. So if there exists a solution, then they're associated. But of course, as soon as you get to dimension 5, then this becomes a kind of quintic, and then it becomes quite hard to solve. So it becomes more difficult in higher dimensions to figure out what exactly, I mean, to write them in terms of things that you understand. But that's what the Chern number inequalities are. It's quite an interesting part of the story, I think. But somehow it's slightly orthogonal to this variational point of view.
Okay, any further question? If not, let's sense the speaker again.